Let's draw the Lewis structures of more complicated molecular species. Let's first start off with water. So water is H2O. So hydrogen, we'll start off with, is happy at 1, but we've got 2 of them. So we got to have 2 valence electrons for the hydrogen. Oxygen is happy at 6. We only got 1 oxygen. So our goal is to get 8 valence electrons around the water molecule. So we're going to make oxygen our central atom. Okay, it's no point in making hydrogen the central atom because we don't know which of the 2 hydrogens we want to make central. And we're going to bond our hydrogen here and a hydrogen here. All right, so 1, 2, 3, 4, and then 5, 6, 7, 8. I'm going to put the 2 lone pairs on the oxygen because it can accommodate it. Hydrogen being really small and happy at only 1 really cannot do anything. And so that would be the structure of our water molecule. Oxygen is a molecule that is very electronegative. So this is an example, classic example of a polar molecule. You see this bond is not a 50-50 sharing. The oxygen, like a vacuum cleaner, is going to suck the electron density of this bond going this way. Same thing can occur on the other end too. So we have at one end of the molecule a partial positive charge on both hydrogen ends. And in the center of the molecule we have a negative buildup of partial charge. So this is an example of a polar molecule where one end is partial, keyword partial positive, and the other end of the molecule, the oxygen side, the oxygen central part of the molecule, is partial negative. This is not how water looks like in 3 dimensions. We can actually get a more refined 3-dimensional structure looking at the central atom of oxygen. So here we have 2 bonds and 2 lone pairs. So those lone pairs also going to affect the 3-dimensional structure. So 2 bonds and 2 lone pairs. This is where we're going to look at our table here. Again, table 10.2 if the central atom has lone pairs. Table 10.1 if there are no lone pairs. And 2 bonds and 2 lone pairs. Okay, 2 bonds and 2 lone pairs. It's going to be, we're going to look at the geometry of the molecule now, bent. Okay, so this molecule has a bent structure, and you can see here 1 lone pair goes that way, 1 lone pair goes the other way, really bends the molecule. So you can imagine taking a linear molecule and bending it. That's what the 2 lone pairs do. Okay, all the time many people would think water is a straight line. It's a molecule that's linear. The 2 lone pairs prevent that from happening. They significantly distort the molecule. So 2 bonds, 2 lone pairs has a molecular geometry that's bent. Okay, so I'm just going to bend the molecule. Okay, take a line and bend it. Those lone pairs are going to be housed in different lobes and orbitals of the oxygen atom. And so the molecular geometry is bent. It's a polar molecule, as we've established before. What about the hybridization scheme? 2 plus 2 is 4. So we're going to take 1 of S, and then how do we get 4? We're going to take 3 from the P. So this is an sp3 hybridized oxygen. An sp3 hybridized oxygen, the bond angle here is going to be something very different. I forget at the top of my head. I want to say 107 to 108 degrees. That's not the key point here. If you want to compare to our previous video, the sp3 tetrahedral carbon was a perfect 109.5. The sp3 hybridized nitrogen with 1 lone pair had a really messy bond angle that I'm sure you can look up in a textbook. And with 2 lone pairs on the oxygen, the sp3 hybridized oxygen has an even more messy bond angle, again because of the bent shape caused by the 2 lone pairs surrounding the central oxygen atom. So water is a polar molecule, sp3 hybridized oxygen, and the molecular geometry is bent.